An ideal monoatomic gas undergoes a cyclic process ABCA as shown in the figure below. Find the heat Q transferred to the system during one complete cycle. From B to C is an adiabatic process. The gas we consider now is a monoatomic gas. That means the molar specific heat at constant volumes of the gas will take the values of the 3/2R, where the R is a gas constant. Now we start to evaluate the heat transfer for the three thermodynamic processes shown in the diagram. From B to C, the process is an adiabatic process. From C to A is isobaric, and from A to B is isochoric, because we are now analyzing the PV graph. Since the B to C is an adiabatic process, that means the heat transfer to the system would be equal to 0. So that means QBC is equal to 0. The process from state A to state B is isochoric, so the work done is equal to 0. Based on the first law of thermodynamics, then the QAB will be equal to the change of the internal energy when the state change from A to the B. To evaluate the internal energy change when the gas evolved from the A to the B, we use the NCV delta T, where the N is the number of mole of the gas, CV is the molar specific heat at the constant volumes, and the delta T is the change of the temperature. The CV value for the monoatomic gas is 3/2R. When the state changes from A to B, this is the isochoric heating. The temperature increased. So that is why we have this delta T here. But we do not know what is the delta T that is not given in the questions. In the questions, we only know what is P1, P2, V1, and V2. Although all these four quantities, the exact value is not given, since the symbols is given in the graph and in the questions. So that means this P1, P2, V1, V2 are considered as a known quantity, and there is no T given. So that means this delta we cannot evaluate the QAB directly from the delta T. What we can do now is that to change the NR delta T into the delta PV based on the equation of state PV equal to nRT. From this equation, we can know that we can see that when the T is changing, while the N and R is a constant, when the T is changing, it will cause the P to change. We can also see from this graph, the pressure is increased from the P1 at the state A to the P2 at the state B. At the same time, the volumes is fixed as at the V1. That is why we can substitute this nRT by delta PV. Now V we change to the V1, and the delta P is the P2 minus the P1. So this is the expressions for the Q that we want to find for the process A to B, isochoric heating from A to B. This is a Q we obtained for this process. For the process of the C to A, which is the isobaric coolings, we have the QCA equal to NCP delta T. We can use this formula NCP delta T to directly evaluate the QCA instead of using the first law of thermodynamics. We have the formulas to directly evaluate the Q for the process CA, which is NCP delta T, where the Cp is the molar specific heat at the constant pressure for the gas. Okay, delta T, this one from C to A, the temperature actually is dropping, so that's why we know that this is the isobaric cooling. The Cp value for the monoatomic gas is 5/2R. So now we have QCA equal to 5/2 nR delta T. Again, since we do not have the informations about the delta T, so now we again use the PV equal to nRT to substitute this nR delta T by the P delta V. So now this change of the temperature will cause the volumes to change, but the P is constant. This is a bit different from the process from A to B that we discussed just now. The case we discussed just now for this isochloric, when there's a change of the pressure, it causes a when there's a change of the temperature, it causes the pressure to change, while the V is constant. But now in this case, the change of the temperature causes the volume to change, but the P now is constant. Okay, there are differences for the process of AB and the process of the CA. So now we can substitute the nR delta T by this P1, which is a constant, multiply with the change of the volume. Now is the V1 minus V2. V1 is the final volume. V2 is the initial volume. So we take V1 minus V2. So now this is the Q, the heat transfer when the state change from the C to the A. We have this QCA equal to 502 P1 times V1 minus V2. Now let us list out the result that we have for the heat transfer in the three processes that we analyzed just now. For the QAB from A to B isochloric heating, the Q is 302 P2 minus P1 multiplied with V1. QBC, this is since it is adiabatic, so it is equal to 0. And the QCA is isobaric cooling, so it is 502 P1 times V1 minus V2. Now, since this P2 is larger than P1, we know that this QAB will take the positive value. QCA, since V1 is smaller than V2, then we know that this QCA will take the negative value. So this is positive, 0, and this is the negative value. If we sum up all these three terms, we'll get the total heat transfer for one complete cycle. So we substitute, we'll get this 3/2 P2 V1, okay, will give us the first terms, and 3/2 P1 V1, which is negative, can add up with this 5/2 P1 V1, which is positive, to get the second term, which is the P1 V1. And the third term is come from this 5/2 P1 V2, and it is a negative in front. So we have the third term. So this is the total heat transfer during one complete cycle, when the state of the gas change from A, B, C, and then back to A. This is the total heat transfer. Since this QAB is positive value, while the QCA is the negative value, after we sum up these three Q to get the total Q for one complete cycle, we would like to know whether this Q will take the positive or negative value. Because we do not know what is the relationship between the P2 and P1, that means let's say how large is the P2 compared to the P1, and also we do not know what is the relationship between V1 and V2, how large the V2 compared to the V1. That means we are not able to know whether this QAB is larger than QCA or smaller than QCA. So that means we do not know whether this Q will take the positive or negative value based on these expressions. But if we apply the first law of thermodynamics to the whole cyclic process, then we can know that since in the cyclic process, the internal energy change is equal to 0, and the work done is equal to the enclosed surface area, which is the positive value in this case, because the arrows in this diagram, in this graph, is in the clockwise directions. So the work done, net work done for one complete cycle is positive value. Then based on the first law of thermodynamics, we know that this total heat transfer in the complete cycle should be positive value. So that means these two terms in these expressions, these two terms should be larger than, first two terms must be larger than the third terms to get the positive value. Or we can know that this QAB must be larger than the QCA. So that is why the question asks that what is a Q transfer to the system. Although from this question we know that the Q for the complete cycle should be positive value, but we need to analyze what is the reasons the Q for the complete cycle is a positive value. We can know that actually based on this first law of thermodynamics, if we apply it to the complete cyclic process. But if we analyze it one by one for three processes, and then based on these three expressions, actually we cannot know which one is bigger, QAB bigger or QCA bigger. So the better ways is to apply the first law of thermodynamics to the entire process to know that the total Q should be positive value. So that means the Q is transferred to the system.